We have been studying how the Markov property of response vector of dynamical systems driven by white noise excitations can be formulated in terms of Fokker-Planck equation. We will continue with this discussion. So, what we did was we formulated the governing equation for the time evolution of the transition probability density functions, and we showed that for linear multi-degree freedom systems under white noise excitations, we can obtain complete solution that involves both steady state and transient regimes, and the result that we obtain agrees with what we got using a Duhamel integral approach earlier. Similar solutions are also possible for first order nonlinear differential equations of this kind governed by white noise, driven by white noise. Here steady state solutions can be obtained quite easily, but the transient solutions need to be obtained using series expansion methods by seeking a solution in a variable separable form. But for more general class of problems, even single degree freedom systems or multi degree freedom systems, it is often not possible to exactly solve the governing Fokker-Planck equation. Nevertheless, for a certain class of problems, the steady state solutions can be obtained, and I showed that for this class of systems, that is where nonlinearity is in damping as well as stiffness, but the nonlinearity in damping is a function of the energy or it is a system that is sum of kinetic energy and potential energy. For this problem, we showed that the steady state solution can be obtained exactly. And similarly, for a class of multi degree freedom systems, I demonstrated that such exact solution for steady state solutions can be obtained. There are broader class of dynamical systems where exact solution to the governing Fokker-Planck equations are possible, but I will not get into that. So, we will move on now with the next topic. We also considered the formulation of moment equations. So, for systems governed by this general stochastic differential equation, this is the Fokker-Planck equation, and based on this we can derive the time evolution of moments where h is a function of x of t, and we derived this equation in terms of the drift and diffusion coefficients, and I formulated these equations specifically for a linear first order system and a single degree freedom linear system driven by white noise. Now, let us continue. We will consider now a first order nonlinear system x dot plus beta x plus alpha x cube is equal to w of t, where w of t as before is a white noise, and we write this in terms of a stochastic differential equation as shown here. Dx of t is minus beta x dt minus alpha x cube dt plus dbt. So, the drift term will be minus beta x minus alpha x cube, and g will be g d g transpose will be d. So, the moment equation has this general form, d by dt of expected value of h is given by this, and suppose if we now focus on expectations of the kind m k is x to the power of k of t. So, the equation for m1 dot is shown here. You carefully look at the right hand side, the equation for m1 now has the term m3. This m3 is nothing but expected value of x cube. Now, you look at the expression for m2, that is expected value of x square, that is mean square value. M2 dot, if you look at on the right hand side, I have m4, which is expected value of x to the power of 4. Similarly, you look at equation for m3, which is expected value of x cube, it has expected value of x to the power of 5 on its right hand side. So, this the moment equations of this kind here form an infinite hierarchy of equations, such that at no stage we get sufficient number of equations, so that we can solve the problem numerically. Suppose you want to find m1, you need to know m3. Moment you write equation for m3, you end up needing m5. You write equation for m5, you need equation for m7 and so on and so forth. So, this problem is known as closure problem. So, moment equations form an infinite hierarchy of equations which at no stage provide sufficient number of equations to solve for the moments. This is known as closure problem. This is a characteristic feature of moment equations of nonlinear systems driven by random excitation. Now, we can develop approximate methods to solve this infinite hierarchy of equations if we ad hocly close this hierarchy by invoking some assumption. For example, after deriving equation for M1 and M2, I can assume that all other higher order moments M3, M4, M5 etc. are related to lower order moments as if the x of t is a Gaussian random process. If you do that, it is known as Gaussian closure approximation. Okay. So, it is in some sense equivalent to linearizing the governing differential equation because Gaussian responses are characteristics of linear systems under Gaussian random excitations. Other ways of doing it would be to assume general form of probability density function of the response, and we can close at an arbitrary level. We can go up to M4 following this hierarchy of equations, and equation for M5, M6, M7 etc. can be assumed to be related to these first 4 order moments again following certain postulated probability density function. The other choice would be to neglect cumulants beyond a specific order. We can simply say that fourth cumulants beyond third order are all 0 or fourth order are all 0, and that helps us to arrest the hierarchy of equations and get sufficient number of equations to solve the lower order moments. These are ad hoc procedures, but nevertheless they are widely discussed in the existing literature. The closure problem can occur, it indeed occurs for non-white excitations also. We have been talking about white noise excitations, but suppose if you consider a Duffing oscillator under a random excitation, this can be a band limited noise, stationary 0 mean random excitation. Suppose I am interested in mean of the response, I can take expectations on this equation. So, I get m into expected value of x double dot plus c into expected value of x dot, so on and so forth. Here I get alpha into expected value of x cube is equal to expected value of f. Now, when you are writing equation for expected value of x, you are getting now expected value of x cube in your equation. Now, similarly, if you want to write now an equation for autocovariance or autocorrelation between x of t and x of t1, I can multiply this equation by x of t1 and take expectation. So, I get m into x of t1 x double dot of t expected value plus all this, and here I get alpha into expected value of x of t1 x cube of t. This is, so in terms of autocorrelation of x, I can write this as dou square rxx dou t square c dou rxx dou t plus k rx rxx t comma t1 plus a higher order moment which at this stage I do not know. This is actually, you can call this as a fourth order moment which is not known. Suppose you want to now overcome this difficulty and multiply this equation by x cube of t and try to get an equation for expected value of x of t into x cube of t1. When you multiply this with x cube of t, you will get x cube of t1 and x cube of t. So, that means a sixth order moment will appear in your equation. So, again this forms an infinite hierarchy, and this is a well known problem known as closure problem. So, moment equations are difficult to deal with in nonlinear random aberration. Now, what happens if there is a parametric excitation? So, here I consider x double dot plus a2 x dot plus a1 into a white noise into x plus another white noise w2 of t. Now, here you can assume initial conditions are specified, and I can recast this into the stochastic differential equation form as shown here, and this matrix now the so called G matrix has a term now minus x1. So, that means one of the system states multiply the noise terms. Now, we can write the moment equations for this, and now it would be of interest to know whether there will be a closure problem for this case. In fact, if you try to solve the governing Fokker-Planck equation here, you would not be able to solve this problem. There are no exact solution to the evolution of probability density function for this class of problems. So, there is indeed a difficulty, but how about moment equations? Well, if you now write an equation for M10, so the notation that I am following is M R S is expected value of x of t to the power of r, x dot of t to the power of s. So, M10 is nothing but expected value of x of t. So, M10 I get on the right hand side M01. So, similarly if I write M01 I get on the right hand side M01 as well as M10. So, if you look at now the equation at the mean level, so this is expected value of x, this is expected value of x dot, we get a closed set of equations. There is no problem here, because on the right hand side I have nothing other than expected value of x and expected value of x dot. So, I can solve this problem and I can get exact solutions. Although the governing Fokker-Planck equation for the evolution of probability density function I am unable to solve, but for the moments I get exact equations which are solvable. How about higher order moments? You now look at M20, which is expected value of x square of t. You get on the right hand side 2 M11, which is autocorrelation, the correlation between x of t and x dot of t. Similarly, M11 dot if you write on the other right hand side I get M02, M20, M11 etc. How about M20? This is M02. I get here an equation which is again contains terms only up to second order. So, that would mean in this case there is no closure problem. Okay. So, you look at first order moments, on the right hand side I have only terms which are first order in nature. You look at second order moments, on the right hand side I have terms which are basically at the second order. See here M02, M11, M20. So, that means moment equations are closed and hence can be evaluated exactly, at least numerically. So, in this particular case we get the approach that we are discussing forms a source of an exact solution. Now, how about steady state here? So, for systems driven by parametric excitations, as we know there is no guarantee that system is behavior would be stable. So, asymptotically as time becomes large we do not know whether steady state is reached or not. But nevertheless if we assume that a steady state indeed exists, we can get the solutions for M01, M10 etc. So, M01 and M10 are 0, M20 I get certain expressions. Now, the question arises whether these steady state solutions are realizable. They may not be realized, they may be unstable. So, what we do? We give a small perturbation to these moments and see whether the perturbations decay in time or not. That means, I study now the stability of moment equations, which are a set of deterministic equations. So, that can easily be done. For example, if you have a set of equations which is y dot is equal to ay plus b and you give a perturbation y plus nu, where nu is a small perturbation, I can get an equation for time evolution of nu, which is nu dot is equal to a nu. So, if you now seek for this set of equations a solution of this form nu naught exponential st, I get an eigenvalue problem governing nu naught and s, and we can show that the solutions are stable provided the real parts of the eigenvalues of A matrix are non-negative. No, for stability they are non-positive. Okay. If it is 0 the solution do not grow, but if it is negative the solution decays. Okay. So, in any case we can form this kind of equation y dot equal to ay plus b from the governing moment equations, and we are able to study now the stability of response moments. The stability of response moments need not guarantee the stability of sample paths of the system. It only means mean, standard deviation, variance etc., covariance whatever we are discussing are stable. It need not mean that samples of x of t need to be stable. So, that has to be borne in mind, and if you want to study stability of samples there is altogether a different approach that we are not discussing in this course. I have discussed till now equations for time evolution of moments where I am considering only one time instant. Okay. Now, how about second order moments or equations for two time moments? So, for example, let us consider n equal to 2, it can be 3, 4 etc., but for the purpose of discussion we will consider n equal to 2. Now, this is the equation dx of t is f of t x of t plus g dbt etc. Now, this is a governing Fokker-Planck equation and this is a transition probability density function. Now, there are two time instants t and t naught in the problem already. Suppose if I now consider expected value of x1 to the power of m of t and x1 to the power of n at t naught. So, this can be written as x1 to the power of n, n1 to the power of n, x1 n1 t comma t naught dx1 d eta 1. This is a definition of expected value. For this joint density function, I will now write it as a marginal density of a 4-dimensional joint density function. Okay, that is this density function, I am writing it as a marginal of a 4th order density function. Now, we can therefore look at this 4-dimensional probability density function and use Markov property and write that in terms of the transition probability density function and a second order density. Actually, this is first order, eta 1 and eta 2 are elements of a vector random process which is Markov, right. So, x1 to the power of m, x1 to the power of n t naught is given by this now, and if we now call a part of this integral, a part of this integrand as say nu of x1 comma x2 t comma t naught as eta 1 to the power of n and the only this term is retained, that means I look at only terms involving integration with respect to eta 1 and eta 2 and that integrand I will call it as v or nu. Now, the requisite moment can be written as x1 to the power of m nu dx1 dx2. Okay. Now, where nu is given by this. Now, in the governing FPK equation, we can see that the FPK equation is also satisfied by this function nu, because this involves x1 x2 t and t naught, and if I substitute, if I carry out this integration with respect to eta 1 and eta 2, this equation is not affected because eta 1 and eta 2 are not the independent variables here. So, therefore, it is immediately follows that this the function nu is also satisfied by the same operator, right. Now, how about initial conditions and boundary conditions? So, this now I have a Fokker-Planck like FPK like equation where dependent variable is this function nu. I can establish the initial condition by considering the definition of nu at t equal to as t goes to t naught, and I get this as x1 to the power of n p y1 y2 t naught comma t naught. So, this is a fairly smooth function. So, it is a good way to specify the initial condition. Then I can actually solve this problem in principle. So, that would mean using FPK equation not only I can formulate a strategy to solve one time moments, but also two time moments, and by the same token higher order moments can also be, equations for higher order moments also can be set up. I will not get into the details of the solutions etc., but we will now move on to a related topic, what is known as backward Kolmogorov equation and reliability function. So far we have been looking at Fokker-Planck equation where the independent variable is t and x, and we assume that system starts from t equal to t naught and t is greater than t naught. So, the independent variable is greater than t naught, in that sense it is a forward equation. Now, if we treat t naught itself as an independent variable along with the associated x naught, then we get another equation known as backward Kolmogorov equation. It turns out that backward Kolmogorov equation is useful for studying first passage times. So far what we discussed was the probability density function of the response and its moments, but this description does not help us to solve the more important problem of first passage time and extremes and so on and so forth. But the backward Kolmogorov equation assists us to tackle that problem. So, there are two references, this one is a book by Professors Lin and Kai, and other one is a book by Professors Cox and Miller, which has certain useful background to this discussion. Now, I will start with discussion on a scalar random process. So, let x of t be a scalar Markov process, and I take 3 time instant t1, t2, t3, and I have this equation which is the Chapman-Kolmogorov equation, which the transition probability density function must satisfy. So, what I will do now, I will consider this transition from T2 to T3, and I will rewrite the the argument x2 as x1 plus x2 minus x1. That means, I am adding and subtracting x1, and I will now perform a Taylor's expansion of this function around x1. Okay. So, if I do Taylor's expansion around this and retain terms up to second order, I get this equation. That means, this is a function of x2, x3, t2, t3. I am performing Taylor's expansion only around x2. Okay. x2 is written as x1 plus x2 minus x1. So, I am expanding this around x1. After doing that, I will substitute that back into the Chapman-Kolmogorov equation and carry out that integrations by parts, and if we do that, this is a reasonably straightforward exercise. We can recast the equation as 1 by delta t. I can transpose some of the terms to the left hand side and divide both sides by delta t, and I can write this as the kind of 1 by delta t into transition from x3 t3 x1 t2 x3 t3 x1 t1 plus these terms which I have displayed here. Now, if you allow delta t to go to 0, we get now the time derivative with respect to t1, that is dou p by dou t1 plus some, this is the incremental moments alpha 1 x1 t1 dou p by dou x1 plus half alpha 2 x1 t1 dou square p by dou x1 square, where p is now the transition from t1 to t3. So, in the standard, this is known as the backward Kolmogorov equation. In the standard form, the above equation is written as dou p by dou t naught as minus alpha 1 x naught t naught dou p by dou x naught minus half alpha 2 dou square p by dou x naught square, where p is probability density function x comma t x naught t naught. This is called backward, as I said already, because the independent variable t naught is less than t. Initial conditions as t naught, t goes to t naught, it is a Dirac delta function, and typical boundary conditions as x naught goes to plus minus infinity, this goes to 0. Now, a vector version of this equation can also be set up. This is straightforward, and logic is same for its derivation, and this is displayed here. So, you should notice that now the independent variables are t naught, x naught and x naught and t naught are the independent variables. Now, when to use forward equation and when to use backward equation, right? The same transition density functions satisfy both the equations. So, when do we solve forward equation and when do we solve backward equation? If we are interested in probability density function of x of t for a given initial condition, we use forward equation. That means, you start with t equal to t naught with a given initial conditions, and you want to know what is probability density function after some time t, you use forward equation. But if you are interested in knowing if the trajectories originate, if we are interested in the PDF of time for first passage across a threshold, we consider the backward equation. I will explain this further. So, what that means? So, we talk about now first passage times. Now, let us consider the scalar SD. Now, I am considering a scalar function dxt is f of x dt g of x dbt with a specified initial condition, and I define a barrier xc, which is a critical barrier, and if x of t reaches that barrier, we say the system has failed. And what I am interested in is, if system start oscillating from a safe region, what is the time required for the first crossing of the critical barrier? That can be used as a descriptor of lifetime of the structure. So, t I define as time at which x of t reaches the critical value xc for the first time, given that x of t naught is x naught and x naught itself is less than the critical barrier. That means, at t equal to t naught, we are starting from the safe region. So, the safe region is x of t less than or equal to xc and unsafe region is x of t greater than xc. So, I define R which is function of x naught, t naught and t and xc and x naught. That means trajectories originate at t naught from x naught and reach a level xc at time t. So, this is probability that x of t stays in the safe region during the interval t naught to t. So, this is nothing but integral of xl to xc probability density of x of t condition x naught t naught dx, which should be interpreted as probability of t greater than t minus t naught. That means first passage time is greater than t if t naught is 0, conditioned on the fact that x of t naught is x naught. Okay. Now, the samples of x of t are such that the first time they reach the level xc they get absorbed, that is x of t equal to xc is an absorbing barrier. Okay. So, what that means is, suppose we are looking at a sample of x of t and imagine that this line as shown here is a sample of x of t. Suppose at say x of t equal to say 3.2 or whatever, I place a barrier. So, you see that at this time instant here the trajectory reaches this level and it gets absorbed. Suppose I am interested in knowing what happens at this time instant. What is the probability that first passage time is greater than 10 seconds if I am interested. So, I have to look at only those trajectories which have not yet been absorbed, and this integration that I am showing here is across only those trajectories which have not yet been absorbed. Okay. So, we have to now place an absorbing barrier for this equation. So, this is the backward Kolmogorov equation, and initial condition is at t equal to t naught, it is a Dirac delta function, and at the critical barrier we say that probability density function is 0. That means we consider only those trajectories which have not yet reached the critical barrier. So, I have shown here a few trajectories of a same random process. This is a trajectory at t equal to 10 second, it has not yet been absorbed. So, this stays in our reckoning, but whereas this goes out, because I am interested in what happens at 10 seconds, okay, at the end of the time period. So, this trajectory has already been absorbed, this survives, this survives, this survives, this is absorbed, this is absorbed, this survives, this survives. So, among those trajectories which have survived, I will do that integration and find out what is the probability that first passage time is greater than 10 seconds. So, how do we write that? Now, I have now got the backward Kolmogorov equation and I have got this expression for R, which is actually the probability that first passage time is greater than t minus t naught, conditioned on the fact that x of t naught is x naught. Now, you can see that the backward Kolmogorov equation is also satisfied by this function R. That means, you perform this integration xl to xc on dx, which is not an independent variable here. The form of the differential equation is will remain the same, because what you will do, you will multiply by dx and integrate over xl to xc, and that first term will be dou r by dou t naught, second term will be f of x naught dou r by dou x naught, and so on and so forth. That means, the backward Kolmogorov operator is applicable even for R, which is the reliability function. R can be thought of as a safety function or reliability function or a survival function, because it means that we are looking at first passage time being greater than a specified time t. So, what are the boundary conditions on it? R of t naught xc x naught t naught is 1. That means, at t equal to t naught, no trajectory has reached the critical barrier. Okay, that translates as one of the boundary conditions. Then R of t comma xc, xc comma t naught is 0. That means, if the trajectory originates from xc, the probability of failure is 1. Therefore, survival is 0, and R being a probability is bounded between 0 and 1. Okay. So, this actually constitutes an eigenvalue problem. So, to summarize that, this is a function that we are looking at. R is probability of t greater than t minus t naught, condition x of t naught equal to x naught. This is the governing partial differential equation. These are the conditions that have to be satisfied, and at the lower end we are placing a non-critical barrier, and we call it as a reflective barrier. Here if trajectories reach this lower barrier, it is not absorbed, but it can return to the safe region subsequently. Okay. Now if we now put tau as t minus t naught, I can make some simplification. This r can be written as tau of xc semicolon x naught. That means probability of t greater than tau condition x of t naught is equal to x naught is what I am looking for, and I get the governing equation in terms of for r in terms of independent variables which are tau and x naught. So again the boundary condition following the similar logic can be written like this. This is the boundary condition on the absorbing barrier, and if we can solve this problem, this set of partial differential equation, I mean this partial differential equation along with this set of conditions, we have now a approach to derive the first passage probability of first passage times. Now the solution for the entire function, that is the probability distribution of first passage time, would require the solution of a partial differential equation. But suppose if we are interested in moments of first passage times, will situation be simpler? So if we look at that, now let us consider the probability distribution function of t, which is probability of t less than or equal to tau conditioned on x of t naught equal to x naught, which is 1 minus r, which is our survival function. So we see that probability distribution function of first passage time is 1 minus the survival function. Now the probability density function is derivative of this with respect to tau, okay, because tau is the state variable. So that will be dou by dou tau of this, and this is minus dou by dou tau of r. That would mean that we have this equation which governs r, and first term here is nothing but the probability density function, right. So I can so the tau as a independent variable now, I mean tau would no longer be an independent variable of this differential equation. This becomes an ordinary differential equation now. So Pt can be written like this. From this, if I now find out the nth order moment expected value of Tn, this will be 0 to infinity tau n, this density function d tau, and I call it as Mn with barrier xc and x naught. So if we look at Mn, this is the definition as I said just now, and we can now use the governing equation and integrate this by parts, and we can see that we reach this equation. Mn is n into tau n minus 1 r d tau. Now we can simplify this by reverting back to the governing equation for r. What we will do is in this equation we will multiply both sides by tau to the power of n and integrate from 0 to infinity. If we do that and rearrange the terms slightly, I get a set of recursive relations for first passage times. Okay. So the equation that I get is recursive relation for moments of first passage times. So n plus 1 into Mn plus f of x naught d by dx naught of Mn plus 1 plus dg of x naught d square Mn plus 1 by dx naught square is equal to 0, and along with this stipulated boundary condition. So we can solve this now sequentially. So if you put n equal to 0, we know that m naught is 1 because that is a normalization condition on a probability density function, area under probability density function is 1, therefore m naught is 1. So I get this simple equation, and this can be solved, and if n equal to 1, what happens is on the right hand side I get m1 which I have already solved. So I get a sequential set of equations which I can tackle one by one, and this set of equations are known as generalized Pontryagin equations, Pontryagin-Witt equations. So they are called GPV equation. How about this is for first one dimensional random process, scalar random process. How about multidimensional case? The same logic would work, the algebra is slightly tedious. So we look at now the vector version of the stochastic differential equation and the associated backward equation, and we now define a safe region. It is no longer a barrier now, it is a region in phase space. So, if x of t belongs to capital omega, we call it as safe, and gamma is the limits of safe region. That means, if you in the phase plane in a 2 dimensional problem, this can be safe and this boundary is gamma and this is unsafe. But this is one proposed one possibility, but there could be other situations. For example, we can have a single barrier problem, this is unsafe, this is safe, or 2 barrier problems, this is safe, this is unsafe, and a kind of a region. So, this is safe, this is unsafe. So, the boundary conditions for the associated the governing partial differential equation have to be formulated based on the physics of the failure criteria that you are interested in studying, right. So, this can be fairly involved. So, in any case we define R as the probability of x tilde colon t conditioned on x naught t naught over the safe region. So, again I place a boundary on gamma, absorbing boundary on gamma, and this equation has to be solved in conjunction with that absorbing boundary. So, if we look at that, again we can consider the governing backward Kolmogorov equation and verify that the reliability function is again satisfied by the same operator, and we have the governing partial differential equation for the survival of the system, probability of survival, and following the same arguments that we used for scalar random process, we can continue to use similar arguments and derive the associated boundary condition. Okay, in principle, therefore, we can formulate the required partial differential equation which governs the first passage time. But now the first passage time is in a region, it is not across barriers as in a scalar problem. So, some of this can be simplified if you introduce tau is equal to t minus t naught, and a simplified version of this can be obtained, and from this we can look at moments of first passage time. The logic is exactly the similar. We start with the PDF of first passage time, probability distribution function of first passage time, and express in terms of express it as 1 minus r, and go back to the equation for r and derive the equation for the moments of first passage times as shown here, and we get this set of equation, that is n plus 1 mn plus L mn plus 1 is 0 for n equal to 1, 2, etc. So, these are the GPV equations for the system. Okay. So, these are again recursive relation, you solve for n equal to 1, then you proceed to n equal to 2 and so on and so forth. In the existing literature, people have used various method of weighted residuals, finite element formulations, etc. to tackle this set of equations, and there are certain numerical approaches that exist which can be used to solve these problems. Now, if you consider what we have been doing till now, based on Markov property of response vector, we derived first the transition probability density function by solving the governing Fokker-Planck equation. Then we derived the equation for one time moments, derived the equation for 2 time moments and so on and so forth, and using backward Kolmogorov equation, we formulated the problem for first passage times. If you recall the discussion that we had when we studied random vibration of single degree freedom systems, we considered properties of envelopes also, envelope and phase processes. So, how to study envelope and phase processes when response process has Markovian properties. So, that is a question that I would like to discuss now, and that is based on an approximate method of response analysis known as method of stochastic averaging. So, what is method of stochastic averaging? It is an approximate method for analyzing lightly damped nonlinear systems under broadband excitations. So, it is it is applicable to weakly nonlinear systems, and under broadband excitations the excitations are not necessarily white to start with, they need to be broadband. If you use this method, you get simplified equations for the envelope and phase processes. So, it leads to simplified models for response envelope and phase processes. And once we get these simplified models, we can show that the envelope and phase together constitute a Markov vector. It can be shown, that I will briefly demonstrate, and if moment you get the Markovian property becomes applicable to envelope and phase, you can write the associated Fokker-Planck equation and get the moments if you want, or write the backward equation and solve first passage problems associated with envelopes. So, you can do lots of analysis. These methods are best suited for studying single degree freedom systems. They are they become unwieldy if we look at multi degree freedom systems, but within the framework of their own limitations, they still provide very powerful means to study envelopes and phase of non-Gaussian random processes. So, that is their main advantage. So, what is this method of averaging? Before I get into that, I would like to cite a reference. This is a review paper written by Roberts and Spanos in 1986. It appeared in International Journal of Nonlinear Mechanics. So, this paper reviews various application of stochastic averaging for solving a class of nonlinear random evolution problems. Now, as a prelude to discussion of stochastic averaging, we will briefly look at what is averaging in a deterministic context. Okay. Now, let us consider the free vibration response of a nonlinearly damped system. The system is u double dot plus omega naught square u is equal to epsilon into f of u comma u dot, and time is reckoned from 0 and initial conditions are specified. The parameter epsilon is a small non-dimensional number. If epsilon is 0, I have u double dot plus omega naught square u equal to 0. So, u of t can be written as a cos omega naught t plus b sin omega naught t, and you can use initial conditions. U of 0 is u naught, would imply a equal to u naught, u dot of 0 is u naught dot, implies b is equal to u naught dot by omega naught, and I can write u of t therefore as u naught cos omega naught t plus u naught dot by omega naught sin omega naught t, and this can be written as some r cos omega naught t plus beta, okay, where r and beta are in terms of u naught and u naught dot and omega naught. So, when epsilon is 0, I can always write the solution as a cos omega naught t plus beta, where a and beta are functions of the specified initial conditions, and the velocity is u dot of t is the derivative minus a omega naught sin omega naught t plus beta. So, when epsilon is 0, these two are exact, and a and beta are constants, they are not functions of time, they are only functions of initial conditions. Now, what we will do is, for epsilon not equal to 0, we will consider a transformation which is fashioned after this exact solution, and we will write that even when epsilon is not 0, I take u of t to be a cos omega naught t plus beta as before, except now that a and beta are functions of time, okay. And u dot of t, I will again make assume the same functional form minus a omega naught sin omega naught t plus beta of t, but a and beta as I said are functions of time. So, if I can derive consistent set of equations for a and beta which satisfy these two equations and the Gowning equation, this will be an exact transformation. At this stage there is no approximation in our discussion. Now, I have u of t is a cos omega naught t plus beta of t, and I will write phi of t as omega naught t plus beta of t, and write u of t as a of t cos phi of t. Now, if this is correct, then a time derivative of u of t would be a dot cos phi t minus a as it is, and cos becomes sin, and derivative of phi is omega naught plus beta dot. But we are taking u dot of t as minus a omega naught sin phi, Therefore, the remaining terms in this equation must be equal to 0. So, what are the remaining terms in this equation? A dot cos phi minus A beta dot sin phi, this must be equal to 0, fine. Now, you consider now u dot is equal to minus A omega naught sin phi, that is what would happen if this condition A is satisfied. From this now I evaluate u double dot. U double dot is what? Minus A dot omega naught sin phi minus A omega naught, sin becomes cos and phi dot becomes omega naught beta dot. So, I get an expression for u double dot and I have an expression for u, and I will substitute that into the governing differential equation and get this equation. A slight reordering of the terms, because two of the terms are going to get cancelled, I get an equation which is B. So, now A and B are the two equations which govern A and beta, which are not known. So, I can solve for A dot and beta dot from these equations. So, the two equations are this A and this is B, and solving for A dot and beta dot, we get A dot as minus epsilon omega naught sin phi into some function of A cos phi and A omega naught sin phi, and beta dot is similarly shown here, minus epsilon omega naught A cos phi and this function. Again, let me emphasize, till now we have not made any approximation, this is exact. Now, we can bring in some arguments based on epsilon being small. If epsilon is 0, A and beta are constants. If epsilon is small, we can expect that A and beta will be functions of time, alright, but they could be slowly varying functions of time. So, they vary much slowly, A of t varies much slowly than sin phi of t itself, because when sin this function completes one cycle of oscillation, the change in amplitude could be quite small. Now, that is A and beta do not change appreciably over the time duration t to t plus 2 pi by omega naught, whereas t changes from t to t plus 2 pi by omega naught, these trigonometric functions undergo dramatic change, whereas the change in amplitude and phase will be quite small if epsilon is small. If epsilon is 0, there will not be any change. Based on that, what we do is we average over a cycle the right hand side of these equations by treating the functions A and beta in the process of averaging as constants. Over a cycle they do not change as much as the functions themselves. So, if I integrate from 0 to 2 pi and take the average 1 by 2 pi, integrate over phi, this integration can be performed by treating A and beta as constants. Okay? If I do that, I get a pair of approximate equations A dot and beta dot, and these we call them as averaged equations. Okay? And many times we can solve for this A and beta or study their fixed points and their stability and so on and so forth. So, I will consider a few examples so that this idea is established in your mind. So, you consider now the first example, u double dot plus omega naught square u is equal to minus 2 epsilon mu u dot. This is the damped free vibration of a linear single degree freedom system. So, here A dot, now this function is specified. So, I can plug that function here and actually calculate A dot, and if I do that I get A dot as minus epsilon A mu and B dot as 0, and if I now solve these equations I get u of t as A naught exponential minus epsilon mu t cos omega naught t plus beta naught. This is quite similar to the exact equation that you would get if you solve this equation by writing the correct complementary function and imposing the initial conditions. The changes would be in terms of the frequency and slight changes in the amplitude. Okay, but by and large this will be a reasonably good approximation to the given problem. A slightly more complicated problem, u double dot plus omega naught square u is minus epsilon u dot into modulus of u dot. So, again I go back now, I look at this equation, I have now the simplified equation for A dot and beta dot, and f is given now. So, I substitute that, I get the equation for A dot and I have to integrate this. As I said, while integrating this, A and beta are taken as constants. So, that means integration is done only with respect to phi, and I get this equation. Similarly, beta dot, if I do, in this case also it turns out that beta dot is 0. Now, this equation A dot is equal to minus epsilon 4 omega naught square A square by 3 pi. We can solve this. This can be written as dA by A square is equal to minus epsilon dt 4 omega naught square by 3 pi, etc., and I can integrate both sides and solve for A of t. If I do this, I get this as the expression for the amplitude A of t, and the beta dot is 0, therefore, beta naught will be a constant. Now, you look at now the nature of A of t. As t tends to infinity, you can see that the denominator here becomes increasingly large, and the amplitude goes to 0. Okay. But the rate at which this amplitude goes to 0 depends on the multiplier here, which is a function of initial conditions. That means, for the same system starting with different initial conditions, you get different rates of decay. So, if you were to compute a logarithmic decrement for this, it would mean the logarithmic decrement is a function of initial conditions, right. Whereas, in a linear system where the concept of logarithmic decrement is basically applicable, the logarithmic decrement is independent of initial conditions. The rate at which the free vibration decays in a linear system is independent of initial conditions. But here that there is a casualty here, that principle no longer holds. So, the rate at which the oscillations decay depends on how you start the system. So, here I have shown different trajectories of the response using the approximate solution obtained using averaging for different values of epsilon, and you can see that as epsilon increases, the decay is rapid, and here I have shown for same epsilon, but with different initial conditions. So, if you compute the rate at which decay is occurring, you can see that it is actually dependent on the initial conditions, especially for small times. Okay. So, this is one of the complex feature associated with nonlinear system behavior. One more example, this is a system with limit cycles. So, here we are considering this equation. So, to understand this, we can write it this as omega naught square u minus u into 1 minus u dot square equal to 0. So, this is our dissipation term. Now, you can see here there is a negative sign here, and we have here 1 minus u dot square. So, if u dot is small, 1 minus u dot will be greater than 0, and we will be dealing with a negative sign for the damping term. That means, motions in the neighborhood of origin tend to grow in free vibration. Whereas, if we start with initial conditions where 1 minus u dot square is large, then the net sign of this term would be positive and the large oscillation will start decaying. So, small oscillations grow and large oscillations decay, that would mean in between them there is a stable periodic solution, isolated periodic solution, and that is known as a limit cycle. So, we can go through the method of averaging and we can get this equation. I have skipped the details, you fill up the details, it is an exercise. So, I get A dot as this, and we can solve this equation, and if you do that we get beta as beta naught and A as this. The time is sitting here. So, as t becomes very large, this function becomes 0 and I am left with 4 by 3 omega naught square root of that as amplitude of A of t. So, that captures the qualitative feature of the response that we expect even before solving the problem. So, this is a solution, and as t tends to infinity, we get 4 by 3 omega naught square root of that into cos omega naught t plus beta naught. This is the amplitude of steady state oscillations in free vibration is independent of initial conditions. Contrast this with the response of undamped linear single degree freedom system. You take undamped single degree freedom system, the solution of that system is periodic, but the amplitude is function of the initial conditions. So, here there is no forcing, solution is periodic. So, in that sense it is similar to an undamped free vibration, but the amplitude of free vibration in periodic state is independent of initial conditions. So, that is where the nonlinearity comes in. So, this is one trajectory where the solutions has originated here and they are growing, and this is my limit cycle. So, this is phase plane plot, velocity versus displacement. A small initial condition, the solution grows and reaches this outer circle. Here the solution originates from this point, a large initial condition, and decays, it moves in this direction and it spirals down, and I get the limit cycle. This is the limit cycle. So, that means limit cycle here is approached from outside, large oscillations decays to that stable limit cycle. Now, this is time history of x of t, where in the first case where motion started with a small value and it is now growing to reach the amplitude of limit cycle oscillations. In this case the solution is starting with a large initial condition, it is now decaying to reach the limit cycle oscillation. So, it is moving towards the limit cycle from the outside, whereas in the previous case it was from inside. Okay. So, this is the behavior of nonlinear systems without any random excitations, where we have used the concept of averaging. So, in the next part of the lecture we will consider how to implement this averaging principle if there is noise present or the system is driven by excitation, random excitations. So, we will consider that in the next lecture, and we will close this lecture at this juncture.